When an engineer designs a new drone propeller, the process is precise. They create a digital model, and software analyzes its physics, how it vibrates, how air flows over it. This analysis can take hours. If they then adjust the design, making it slightly wider or changing the angle, the software cannot simply update its analysis. The entire computation must start again from the beginning, as if the previous one never happened. This is the standard for every simulation tool in existence. This new research changes that. It builds one unified AI model that already contains the physical properties of every possible propeller design in a given range. You are no longer analyzing a single shape, but an entire field of possibilities at once. The old way of simulation was brittle. It locked the physics of an object into one frozen shape. If you changed the design even slightly, the entire mathematical framework had to be discarded and rebuilt from nothing. This made exploration painfully slow. They introduced a model that wasn't tied to one shape, but could understand an entire family of designs at once. They used a neural network to create a single, continuous mathematical fabric. You give it a set of numbers that define a shape's parameters, and it instantly tells you that shape's physical behavior. The central challenge they overcame was one of tracking. When a shape morphs, its core physical properties can unpredictably swap precedence. This instability would cause conventional methods to fail. Their solution was a new way to consistently track each behavior, ensuring the model never gets lost. This creates a stable and reliable map of the entire design space, which is the foundation that makes automatic optimization possible. With this reliable map, the search for the optimal design becomes straightforward. You specify a goal, and the system identifies precisely which changes will improve the design. It systematically follows this path until it arrives at the best solution. The old method had no sense of direction. You could simulate one design and then another, but each was a separate, isolated calculation. There was no connection between them. You were waiting for the simulation to finish and hoping it was an improvement. One of the most compelling demonstrations of this method was its ability to redesign a robot's leg for speed. They began with a simple leg and a basic walking rhythm. The system could adjust the leg's proportions, its width, length, and thickness. Through guided discovery, it would simulate walking, measure the distance, and then calculate exactly how to adjust its shape for improvement. The simulation understood cause and effect, enabling precise adjustments each cycle. It eventually found a design that walked 18 times faster using the same simple controller. However, this power comes with a cost. Building this intelligent model requires significant upfront computation. For complex objects, this can mean a training period of dozens of hours before any exploration can begin. It is a powerful tool for deep optimization, but not yet for instant, spontaneous design.